So I'm Robert Koldebank. I'm one of the technical program chairs, along with Alon Olitsky, who's sitting down here. And I'm happy to say that we have no last-minute announcements this morning about changes of rooms. I do want to remind you that there's a poster session outside on the third floor after the plenary lecture. And I think that all that's left for me to do is to introduce Professor Toby Berger, who is going to introduce today's speaker, Raymond Yeung.
Thank you, Rob, and good morning, everybody. This morning's plenary speaker is Professor Raymond Yeung from the Chinese University of Hong Kong. And Raymond was born in Toronto, Canada, and raised there. Then his entire higher education took place at Cornell University in Ithaca, New York, where I had the distinct pleasure to teach him subjects including information theory. And I had what is proving to be the steadily increasing honor of supervising his work on the master's and PhD level. Raymond has asked me, please, not to make a list of his accomplishments at this moment, so I will do that. I, however, feel compelled to mention, though I suspect that you already know it, that Raymond is, I believe, universally recognized as the founder, or certainly the co-founder, of the exciting new discipline of network coding. However, Raymond is not going to talk to us about network coding this morning. His talk is entitled Facets of Entropy. When I teach information theory, I'm not very Socratic about it. I just get up and lecture and take an occasional question, but don't ask questions to the class much, if ever. But there's one exception. Every time that I teach information theory, after about 4 or 5 weeks, when the information measures have been introduced and the lossless source coding theorem has been proved and Huffman coding has been done, and you see the connection between the underlying ideas and the practicality of it, and you see theorems that work for stationary sources and imbue the entropy rate with its significance, the subject begins to fall together, and at that point I ask my question, which is, well, do you see anything different about information theory from all of the other courses that you have taken? First of all, they're kind of shocked by the fact that I've even asked them a question, but unless they have spoken to somebody from a previous year, there's only one time I think I got my answer back at me right away, but I think it came through an earlier student. So the usual kind of answers are, well, you know, you do a lot of things with inequalities, and in most of our courses we see mostly equalities and rarely inequalities. I say, yes, that's true, but that's not what I'm looking for. So then they say, no, you prove much more in class than is done in most of our other subjects. I said, yes, but that's not it. So then they say, what is it? And I say, information theory is beautiful. And this is something that I really believe, and perhaps the most beautiful thing that can happen for a professor and for somebody who is devoted, like all of us here are, to the subject of information theory, is to see one's own students pick up on that idea, make it the centerpiece of their careers, and succeed and enjoy the beauty of that subject. Raymond Yeung certainly personifies that, and so I give you Raymond Yeung. Thank you.
Hey, good morning, everybody. First, I would like to thank the organizer for inviting me to give this talk, and of course, it is my greatest honor to be introduced by Toby. Now, today I'm going to tell you what I know about the entropy function, which I've been studying for almost 15 years. Okay, The plan for this talk is that I'm going to tell you some preliminaries of the subject, and then I'll move on to talk about the connection between the entropy function and various fields of studies in information science and also in physics. Okay, first a little bit of notation. We're going to use script n to denote the set of integers from 1 to n. We are going to use omega to denote a set of random variables, which in fact is x1 up to xn. Okay, and where xi is a discrete random variable at this point. Okay, it will become something else later. Now, we all know that we can define entropy for a discrete random variable. And for more than one random variable, we have the joint entropy. And in information theory, entropy is the measure of the uncertainty contained in a discrete random variable. And this is not something arbitrary or convenient, but it is something really justified by fundamental coding theorems. Now, for n random variables, there are 2 to the power n minus 1 joint entropies. For example, when n is equal to 3, we have 7 joint entropies, and they are entropy of x1, x2, x3 individually. We have the joint entropy of x1 and x2, x2, x3, x1, x3, and then a joint entropy of x1, x2, and x3. Okay, we are going to write x sub alpha as xii in alpha, where alpha is some subset of the set of integers from 1 up to n. For example, x sub the set containing 1, 2, and 3 denotes the collection of random variables x1, x2, and x3. And for a particular collection of random variables, omega, we define the function h of alpha, okay, to be the joint entropy of the collection of random variables indexed by alpha. For example, entropy of h of 1, 2, and 3 is equal to x1, x2, and x3. I'm not sure whether you can see the laser pointer because this room is so big. We probably need a bigger laser gun for that purpose. Now, upon defining the value of this h function of the empty set to be 0, which is a reasonable definition because the entropy of an empty collection of random variables is equal to 0, we have formally defined a set function h from the power set of script n to r. Okay? And this function is called the entropy function of omega, which means that when I give you an index of the random variables, it returns the joint entropy of that collection of random variables. Now, it is well known that for any collection of random variables omega, the corresponding entropy function satisfies the so-called Polymatroid axioms. Specifically, for any alpha and beta, which are subsets of script n, we have, number 1, the h of the empty set is equal to 0, which is by definition. And h of alpha is less than or equal to h of beta if alpha is a subset of beta. And also that h of alpha plus h of beta is bigger than or equal to h of alpha intersect beta plus h of alpha union beta. Now, in information theory, in addition to entropy, we also define a conditional entropy, mutual information, and conditional mutual information. The only thing I would like to point out is that all these 3 quantities that are subsequently defined can be written as linear combinations of unconditional joint entropies. And these collectively are called Shannon's information measures. Now, in information theory, we also know very well that all these Shannon's information measures are non-negative, and we call them the basic inequalities, namely that all entropies are non-negative, and mutual information non-negative, conditional entropy non-negative, and conditional mutual information non-negative. Now, these constraints on entropies are sometimes called the laws of information theory because they govern the impossibilities in information theory. In converse coding theorems, we invoke these inequalities every so often. In doing so, what we are actually proving is that certain things are impossible in any kind of information transactions. Now, back in 1986, Nick Pippinger asked the question, are there any constraints on entropies other than the basic inequalities? Now, one thing I think I have missed is that somehow it's missing here. The basic inequalities are actually equivalent to the polymatroidal axioms that I have shown you in this slide. Okay, so the two things are actually equivalent. Although the polymatroidal axioms are more familiar to people in communities like physics. Okay, but in information theory, we are more familiar with the basic inequalities, but they actually are equivalent. Okay, now to formulate the problem properly, I'm going to introduce to you a geometric view of the problem. Specifically, I'm going to introduce to you this region which I'm going to call gamma n star. Now, the first thing to do is we need to fix the n, which is the number of random variables. Now, for each collection of n random variables, the h function defines a vector in the 2 to the power n minus 1 Euclidean space. Namely that for any collection of n random variables, you evaluate all the joint entropies, and that corresponds to a particular point in the 2 to the power n minus 1 dimensional Euclidean space. Now, to simplify our discussion, we are going to call this Euclidean space the entropy space for n random variables. Now, a vector in this Euclidean space is called entropic if it corresponds to the entropy function for some collection of random variables or for some joint distributions. Okay? And then we define in the entropy space the region gamma n star, which is the set of all vectors or points in the space which are entropic. Okay? Now, what is the relation between this region gamma n star of all entropy functions and entropy inequalities? Now, an entropy inequality has the form f of h is bigger than or equal to 0, where h is all the joint entropies. Okay, some function of all the joint entropies are bigger than or equal to 0. And in information theory, we usually consider non-strict inequalities. Now, the relation between such an inequality and gamma n star is the following. We say that the inequality fh is bigger than or equal to 0 always holds if and only if gamma n star is a subset of this set induced by this inequality fh is bigger than or equal to 0. This is all the h in entropy space such that the inequality fh bigger than or equal to 0 is satisfied. Okay? I'm going to show you a picture to illustrate the point. This is the very meaning of what we mean by an inequality regarding entropies is always holds. Okay, this is the very meaning of such an inequality. Now, in fact, since we are dealing only with non-strict inequalities, fh bigger than or equal to 0 always holds if and only if gamma n star bar, which is the closure of the region gamma n star, is a subset of this set induced by the inequality fh is bigger than or equal to 0, and precisely because this region induced by fh bigger than or equal to 0 is closed. Now, this picture illustrates the relation between gamma n star and the inequality we have in mind. So in this picture, the region gamma n star is completely contained in the region induced by fh is bigger than or equal to 0, which means that whatever joint distribution you come up with for n random variables and you evaluate the joint entropies is going to be a point somewhere inside the set. And because this set is completely contained in this region, fh is bigger than or equal to 0, it has to satisfy this inequality always. Okay? So this is the very meaning of the inequality fh bigger than or equal to 0 always holds. On the other hand, if the region gamma n star is not completely contained in fh bigger than or equal to 0, like this one, then you can always find a point here, which is entropic, okay, which doesn't satisfy the inequality fh is bigger than or equal to 0, which means that the inequality fh bigger than or equal to 0 does not always hold. Now, there's a related region, gamma n, which I would like to introduce, and this is the region in the entropy space, which satisfies all the basic inequalities, okay? Namely that all the Shannon information measures are non-negative. Now, because we know that all distributions satisfy all the basic inequalities, we immediately have the relation that gamma n star is a subset of gamma n. Okay? And we say that an entropy inequality fh bigger than or equal to 0 is a Shannon-type inequality if it is implied by the basic inequalities. Namely that gamma n is a subset of the region induced by fh is bigger than or equal to 0. In fact, for for almost 50 years in information theory, we have been relying only on the basic inequalities in proving convex coding theorems. Now, this geometric view of entropy inequalities enables machine proving of entropy inequalities. In fact, the whole thing can be formulated as an linear programming problem. And the following applications have been developed. First, we have the ITIP developed by myself and one of my previous student, Yeung. That was back in 1996. Recently, a newer version of ITIP called XITIP has been developed at EPFL by the group of Digabi and his students. This is quite recent. And the original ITIP was implemented in the MATLAB. The latest version, XITIP, is implemented in C, so it's more efficient computationally and also more system independent. Okay? And by the way, these are the original colors of XITIP, and so Haas can verify that. Now, most recently, I heard from Se-Young Chung at KAIST that he's in the process of developing something called ITTP. Now, the difference between ITTP and the previous implementation is that the previous two implementations are linear programming based, and while ITTP is axiom based. So potentially it can be much more efficient than the previous two implementation. Now, with this geometric view in mind, we can rephrase Pippenger's problem as follows. So the problem is that Pippenger asks can be rephrased as, is gamma n star bar the same as gamma n? Okay, gamma n star bar is the closure of all the possible entropy functions, and gamma n is an outer bound of all the entropy functions. Okay, so the question is whether there's a gap between the two regions. Now, the answer is no, if and only if there exists an inequality, an entropy inequality GH is bigger than or equal to 0, which cuts between these two regions, gamma n and gamma n star bar. And if such an inequality exists, we call this a non-Shannon-type inequality. Now, it is known that gamma 2 star is equal to gamma 2, so nothing unusual happens for 2 random variables. For 3 random variables, already something unusual happens, namely that gamma 3 star is not exactly equal to gamma 3. However, if you take the closure of gamma 3 star, it becomes equal to gamma 3. Now, therefore, if we are looking for unconstrained non-Shannon-type inequalities, they can exist only for 4 more random variables. In general, gamma n star is neither closed nor convex, which is pretty peculiar. But gamma n star bar is better behaved, and in fact, it's a convex cone. Now, in 1998, I worked with Zhen Zhang, who's not here today, and we found the first unconstrained non-Shannon-type inequality, and which has this form, okay, which is kind of complicated, but it involves 4 random variables, x, y, z, and u, and this inequality is satisfied by all distributions that you can come up with for 4 random variables. But this inequality is not implied by the non-negativity of Shannon's information measures. So this is the geometric view of this inequality, which I denote by ZY98. So this is gamma 4 star bar, which is the closure of all entropy functions for 4 random variables. Gamma 4 is the well-known outer bound to gamma 4 star bar. And in between, we have this inequality, which cuts between the 2 regions. So there's actually a real gap between gamma 4 star bar and gamma 4. Now, the question is whether this is just something, some kind of singularity or not. Okay, at that point we were not sure. Okay, but after many years of research by a number of researchers, the picture now has become clearer. So this inequality ZY98 have been further generalized Makarishev et al. In 2002, Zhenjiang himself in 2003, and Matouche in 2007. Oh, by the way, although I was responsible for formulating the problem, I actually played a relatively minor role in discovering ZY98. It was mostly Zhenjiang's credit for that inequality. Now, in particular, Matouche in 2007 showed that gamma n star bar actually is not a polytope, okay? And hence there exists an infinitely many linear non-Shannon-type inequalities. So in fact, the story is that the number of non-Shannon-type inequalities actually are much more than the number of Shannon-type inequalities. Okay. So, in 2006, Doherty, Freiling, and Ziegler have discovered several tens of non-Shannon-type inequalities by means of a search on the supercomputer at UCSD. So basically what they did was that they used the proof technique for discovering ZY98 together with ITIP. They put it on the supercomputer and then crunch it. Okay? And then I think Ken Siegler told me that it took the supercomputer about 1 week to discover one non-Shannon-type inequality. And so this is how I calibrate the computing power of Zhenjiang. Okay? He invented the proof technique himself, and then took another year and a half to find the first non-Shannon-type inequality. Now, in the second part of the, so I finished with all the introduction of this subject. So in the second part of the talk, I'm going to talk about some relations between this region gamma n star and certain fields of studies in information science and also in physics. Now, in this picture, the two kinds of arrows, red and blue. For the red arrows, they are double-ended, which means that there exists a one-to-one correspondence between gamma n star and also and the corresponding subject. And for the blue arrows, it's one-ended, which means that the gamma n star has some implications in these subjects. Now, first, I'm going to talk about combinatorics. I'm going to introduce to you something called a quasi-uniform array. Now, for a distribution P of x for a discrete random variable, a sequence x of length n is strongly typical if the empirical distribution of x is approximately equal to P of x. I think this is familiar to most of you. And for joint distribution, we can define a strongly typical sequences, pair of sequences accordingly. And the relations between these typical sequences can be illustrated by what I call a two-dimensional quasi-uniform array. Now, in this array, the rows represents the typical x sequences. The columns represents the typical y sequences. Okay, and if a typical x sequence is jointly typical with a y sequence, we put a dot in the array. Okay. Now, by the asymptotic equipartition property, we know that there are approximately 2 to the power n times h typical x sequences, and there are approximately 2 to the power n times hy typical y sequences, and the number of dots are approximately equal to 2 to the power n times entropy of x and y. Okay. Now, furthermore, this is just a reproduction of the previous picture. Now, each row has approximately the same number of dots, because here we are talking about strong typicality. So if you go down each row, you'll find that there are approximately 2 to the power n times entropy of y given x number of dots. If you go down each column, it has approximately 2 to the power n times entropy of x given y dots. Okay. Now, so upon doing a very simple counting, we find that the total number of dots, which is the 2 to the power n times entropy of x and y, must be upper bounded by the total number of cells in the array, which is 2 to the power n times entropy of x plus multiplied by 2 to the power n times entropy of y. Upon taking logarithm and dividing it by n, we obtain this inequality, which is very familiar. Entropy of x and y is less than or equal to entropy of x plus entropy of y, and which is equivalent to that the mutual information between x and y is non-negative. So this picture is very interesting because it tells you that the basic inequalities or inequalities about entropy in general is actually about counting. And the inequality is actually about unfilled entries in the array. So this provides a very interesting combinatorial interpretation of some entropy inequalities. Okay. I'm going to show you that this actually gives the whole picture. Now this is the three-dimensional quasi-uniform array. And here, this is a cube which you can cut in three possible ways. You can cut it this way, and this way, okay? And for each cut, you expose a cross-section of the cube. And if in the cross-section you have at least one dot, then the total number of dots is approximately the same, okay, for each cut in the same direction. You can do it this way, and this way, okay? And if you fix a particular point x naught, y naught, okay, which x naught, y naught are some typical sequences, and you poke the cube in this direction, okay, if you run into at least one dot, then the number of dots would be approximately the same anywhere you poke into the cube, okay? Of course, you can poke into the cube in three different possible ways, okay? So this is what I call a uniform, quasi-uniform array. Now, another way to describe the quasi-uniform array is the following. For an n-dimensional quasi-uniform array, if all the dots are assigned equal probabilities, then the projection on every lower dimensional plane has a uniform distribution over its support. So this is an equivalent description of a quasi-uniform array. Now the question is, do quasi-uniform arrays fully capture all constraints on the entropy function? Now I've shown you one example that you can prove an inequality for entropy using a quasi-uniform array. But the question is whether they captures everything that we want. Now the answer is yes. This was proved in the master thesis of my former student Terence Chen, and he showed that all constraints on the entropy functions can obtain through quasi-uniform arrays and vice versa, which means that by studying the structure of this, the combinatorial structure of quasi-uniform arrays, you actually can obtain all possible entropy inequalities. Okay, now I'm finished with combinatorics. Now I'm going to talk about the relation between the entropy function and group theory. Now this again was done in the master thesis of Terence Chen. Now the setup is the following. We let G be a finite group and G1, G2 up to Gn be subgroups of G. And we denote G of alpha to be intersection of Gi, where I is in some index set alpha. And it turns out that G sub alpha is also a subgroup of G. Probability distribution for n random variables, x1, x2 up to xn, can be constructed from any finite group G and subgroups G1 up to Gn. I'm not going to get into the details. Basically, what happens is that if I give you a finite group G and subgroups G1 up to G2, G1 up to Gn, based on this, this collection of groups and subgroups, you can define n random variables x1, x2 up to xn. And upon evaluating the joint entropy of this collection of n random variables, we find that the entropy of x alpha is equal to log of the order of G divided by the order of G alpha. Okay? And one thing to note is that the evaluation of these joint entropies depends nothing but the orders of the group G and the subgroups G1, G2 up to Gn. Now, if we have an entropy inequality which always holds, it holds for this particular distribution. So upon substituting the joint entropies into any entropy inequalities, that would give an inequality in group theory. For example, for this inequality, which is very well known, x1 plus x2 is bigger than or equal to x1 comma x2. What you do is whenever you see h, you replace it by a log, and then you have a fraction. Upstairs, you have the order of g. Downstairs, when you see x1, you replace that by order of g1. And you do the same thing for x2. And for x1, x2, what you do is you put a log here, and then upstairs you have an order of g. And when you see x1 comma x2, you replace that by the intersection of G1 and G2. And upon removing the logarithm in this inequality, we obtain this inequality order of G times order of G1 intersect G2 is bigger than or equal to order of G1 times order of G2. Now, this is a very well-known inequality in group theory, and you can even find this in textbooks in group theory. So there's nothing too interesting. However, non-Shannon-type, quote-unquote non-Shannon-type group inequalities can also be obtained accordingly. For example, if you write out ZY98, which I've shown you in another form, if you write it out in terms of joint entropies, it looks like this, which is, looks a little horrible to me. And this would correspond to this group inequality upon substituting the entropy function by the values obtained for this specific distribution induced by group theory. So it can be proved that the correspondence between entropy inequalities and group inequalities is also one-to-one, meaning that if you can find, if you show that a group inequality holds for all groups and subgroups, then through this symbolic transformation, you can get back an entropy inequality which holds for all joint distributions. Okay, now before I leave the group theory, I would like to illustrate to you the relation between finite group and quasi-uniform array. And that will shed some light on why this one-to-one correspondence happens, although the group theory and entropy functions appears to be two totally different things. Now, the main thing is that the distribution of the elements of a finite group among its subgroups exhibits a quasi-uniform structure, which is illustrated by this picture here. Now, this picture shows the elements of a group. Here, for each cell which is non-empty, it contains 3 dots. So there are a total of 18 dots here, which are the group elements. The first column corresponds to subgroup G1, and the second column and third column corresponds to its cosets. The first row here is a subgroup G2, okay? And the second row and third row corresponds to subgroup cosets of G2. Now, by the Lagrange theorem, we know that the columns of the number of dots in each column has to be the same. The number of dots in each row has to be the same. Okay, because the size of a subgroup and its cosets have the same size. Okay. Now, now this intersection here, which is the upper left corner, is the intersection between G1 and G2. It can be shown that so each cell here corresponds to some cosets of G1 intersect with some cosets of G2. It turns out that for each of these cells, either it contains no dots. If it is non-empty, the number of dots it contains is exactly equal to the number of dots contained in G1 intersect G2. Okay, so that's why you have this quasi-uniform structure. And the only difference between this structure and the structure I showed you previously is that each cell can contain more than 1 dot, but it's basically the same structure. Okay, next I'll move on to talk about Kolmogorov complexity. Okay, we're going to use K to denote the Kolmogorov complexity of a collection of sequences. Hammer et al. In the year 2000, these are a group of researchers from Russia. They show that there exists a one-to-one correspondence between entropy inequalities and Kolmogorov complexity inequalities. For example, we know that this inequality holds for all random variables x1 and x2. So this inequality holds accordingly. Okay, namely that I messed up a little bit because x1 should correspond to small x1. Okay, so small x1s and small x2 are sequences. So the corresponding inequality for Kolmogorov complexity is that kx plus ky is bigger than or equal to kxy. And again, this is a one-to-one correspondence, namely that if you find any inequality which holds for all sequences for Kolmogorov complexity, the corresponding entropy inequality would also hold. Okay. So non-Shannon-type Kolmogorov complexity inequalities can also be obtained. You just translate a non-Shannon-type inequality, whatever it is, into an inequality in Kolmogorov complexity, and it holds for all sequences. Now I turn to probability theory. Now, I'm going to describe to you the problem of compatibility of conditional independence, not in its full form, but in a form which is easier to explain, which I call the implication problem. The question is a given conditional independency implied by a given set of conditional independencies? Okay, for example, suppose we have a Markov chain x, y, and z in this direction, and we also know that x is independent of y. Okay, so the question is whether x is independent of z. It's very clear that this is the case here because y, x, and z relate to each other through y. If x and y are independent, then x and z got to be independent. So this is what I call the implication problem. This is a very basic problem in probability theory, and surprisingly, it's very hard for more than 4 random variables. When I first learned about this problem, I thought, oh, this problem must have been solved at least 15 years ago, but it turns out that it is a very hard problem. Okay, now this is a subproblem of characterizing the region gamma n star because a conditional independence relation is just a hyperplane in the entropy space. Precisely, for example, if we have x independent of y given z, it corresponds to the mutual information between x and y given z is equal to 0. If you express the conditional mutual information in terms of unconditional entropies, it becomes a linear combination of entropies. And this is nothing but a hyperplane in the entropy space. So the conditional independence problem is a discrete problem embedded in a continuous problem. The reason why I call this a discrete problem is because a random variable is independent or not independent with another random variable. But so it is a discrete problem. But the mutual information and that kind of things are continuous measures. So that's why I say that this is a discrete problem embedded in a continuous problem. So in particular, if you can solve if you have a full characterization of gamma n star bar, you also have a solution for this problem. Now, the problem for 4 random variables, the conditional independence problem for 4 random variables was settled by Matouche in 1999 with the help of the following non-Shannon-type inequality. It says that if x is independent of y or y is independent of u given z, then this inequality holds. Some of you may recognize that this is the so-called Ingleton inequality, okay, which does not hold in general for all distributions, but Matouche showed that if this condition holds or this conditional holds, then the Ingleton inequality holds. And this is a non-Shannon-type inequality. So, and matrix theory is a powerful tool for studying this problem because, as some of you may know, that the Ingleton inequality actually came from the Ingleton matroid, from matrix theory. Now, I'll turn to matrix theory. Now, for discrete random variables, we can define entropy. For continuous random variables with a PDF, we can define differential entropy and also joint differential entropy accordingly. Now, in 2006, Chen showed that a differential entropy inequality is valid if and only if the coefficients of the random variables are balanced. I'm going to tell you what it is. And its discrete counterpart is valid. So what it means is the following. We consider this inequality conditional differential entropy of x given y. We want to see whether it is always bigger than or equal to 0. So what we do is we expand it into xy minus hy. Now this inequality, the discrete version of this inequality holds. However, this is not a valid inequality for differential entropy because the coefficients are not balanced, namely that if you count the number of occurrences of x is equal to 1, which is not 0. You count the number of occurrence of y, so you have a 1 occurrence here, but you have a minus 1 occurrence here, so the number of occurrences is equal to 0. So it is not balanced for x. That's why this inequality is not valid in general. On the other hand, this inequality, saying that the mutual information between x and y is valid, is a true statement because if you look at expand it in terms of the joint entropies, you have hx plus hy minus hxy. You count the number of occurrences of x is equal to 0. You count the number of occurrences of y is also equal to 0. So it is a balanced inequality, and therefore it holds. And it turns out that the coefficients in this non-Shannon-type inequality Z198 are balanced. So it is also valid for differential entropy. Now I'm going to discuss a particular distribution, namely the Gaussian distribution. Now any symmetric positive definite matrix is a valid covariance matrix so that it defines the joint PDF of a Gaussian random vector, x1, x2 up to xn. Then we can evaluate the differential joint entropy of this Gaussian vector, and it turns out to be entropy of x plus is equal to 1/2 log 2 pi e to the power n times the determinant of k for this covariance matrix k. Okay? And for any subset alpha of this index set, we can evaluate the corresponding differential entropy h of x alpha to be 1/2 log 2 pi e to the power of the size of alpha times the determinant of the submatrix k alpha. Okay, and then we substitute these joint differential entropies into the well-known inequality for differential entropy, namely that the joint differential entropy is upper bounded by the sum of the individual differential entropies. And this would give the Hadamard inequality. And this has been expounded in the book by Cooper and Thomas. Now, we can apply the same technique and substitute these joint differential entropies into, for example, the inequality Z198, and that would give rise to this inequality, which gives constraints on the determinants of the submatrices. And this holds for all positive definite matrices. Okay. So many other non-Shannon-type determinant inequalities can also be obtained this way. Okay, as long as the coefficients in the inequality are balanced, you can apply this technique and obtain many other non-Shannon-type determinant inequalities. In fact, Terence Chan and I are in the process of showing that all these inequalities implied through the entropy function are all those constraints that you can ever obtain for positive definite matrices. So, but we are not sure at this point. Okay, now I'll talk about the connection between gamma n star and network coding. Now, for single source network coding, the network capacity is completely characterized by the maximum flows in the network. This is well known. Now, for multi-source network coding, the problem is much harder and has been studied by Zheng and myself in 1999, Song, myself, and Tai in 2006. And in 2007, Yeung, Zhang, and myself finally obtained a complete characterization of the network capacity in terms of gamma n star. Now, this is an implicit characterization because we don't know how to characterize gamma n star explicitly. And at the same time, Doherty, Freiling, and Ziegler constructed the first multi-source network coding example whose characterization of the network capacity requires the non-Shannon-type inequality Z198. Now, this is a very interesting result because after the discovery of non-Shannon-type inequalities, we know that it can be applied in probability to solve the implication problem of conditional independence in probability theory. But in information theory, we have no clue what it could mean. And this example constructed by Doherty et al. Is very significant because it shows an application of such inequalities. Now, the construction is based on the Polymatroid. And in 2007, around the same time, Chen and Grant proved a one-to-one correspondence between entropy functions and multi-source network coding problems, which means that every entropy function actually corresponds to some multi-source network coding problem. So from this result, we know that every constraint on the entropy function is useful in some multi-source network coding problems. So all these non-Shannon-type inequalities, whether they are already discovered or yet to be discovered, are useful in some information theory problems. So finally, the implications of non-Shannon-type inequalities in information theory is understood in the context of network coding. Now here I would like to mention a related problem called secret sharing. This is a problem in cryptography which was introduced independently by Blakely and Shamir in 1979. And recently, Baimo et al. Has applied the non-Shannon-type inequality ZY98 to obtain a new law bound in a secret sharing problem. And I just want to remark that secret sharing can be regarded as a special case of secure network coding. Okay, finally, I would like to say something about quantum mechanics, which I know very little about. Now, the von Neumann entropy is an extension of the Shannon entropy to quantum mechanics. The strong subadditivity of the von Neumann entropy, which is analogous to the basic inequalities for the Shannon inequalities, or equivalently the Polymatroid axioms, was proved a long time ago by Leib and Rusky. That was back in 1973. And inspired by the discovery of non-Shannon-type inequalities, Pippinger, who first looked into this problem, came back to the problem and proved that for a three-party system, there exists no inequality for the von Neumann entropy beyond strong subadditivity. So for three systems, okay, you don't have anything abnormal. However, in 2005, Linden and Winter discovered for a four-party system a constraint inequality for the von Neumann entropy, which is beyond the independence of, beyond the strong subadditivity of the von Neumann entropy. Now, this inequality, at this point, is not as strong as the inequality, the corresponding inequality in ZY98, because in ZY98 it is an unconstrained inequality, while this one is a constrained inequality. Okay? But nevertheless, there's something interesting happening. So this is a summary of my talk, which I've shown you for the for those with red arrows. There's a one-to-one correspondence with the entropy function. For those with blue arrows, gamma n star has some implication. So it comes to the concluding remarks. Imre Chisser, an eminent member of our community, advocates that information theory should be an integral part of mathematics, and I cannot agree with that more. And it is now clear to us that constraints on the entropy function has fundamental implications in a number of fields in information science, mathematics, and physics. There exist one-to-one correspondences among the entropy function, group theory, Kolmogorov complexity, and network coding, suggesting that they share the same underlying structure. Although what this underlying structure is not clear at this point, but it's quite intriguing to me. Matroid theory plays a role here and there, in particular in the study of conditional independence and network coding. In particular, when you want to draw a line between what can be achieved by nonlinear coding and linear coding, Matroid theory has a role to play. The relations between these fields need a deeper understanding, as I've mentioned. In my opinion, the combinatorial structure to study is the quasi-uniform array. It's something very basic as far as I understand. And also, non-Shannon-type inequalities in different fields need further understanding. So far, we know that it can be applied in the probability theory. We know its role in the in information theory in the context of network coding, but we don't know too much beyond that. Okay, since I have a little time, I would like to show you some archival materials. Now, in 1998, I received, Zhen Jiang and I received this email from Nick Pippinger. It reads, I've just seen your paper on the characterization of entropy function via information inequalities in the ITIP transactions on information theory. Please allow me to congratulate you on the most beautiful result. I work on a problem of whether gamma n star bar is equal to gamma n during the 80s without any success. I presented it as an open problem at the SPOC, stands for Specific Problems on the Communication and Computation, which was organized by Bellcore in the 1980s. Okay, I believe there were preprint proceedings published by Springer, but they seem to be out of print now. What actually amazed me was that Nick Pippinger, not being an active member in this community, actually looked into this problem some 15 years before Zhen Jiang and I did. And so there are some really smart guys out there who are very concerned about information theory. Okay, this is subsequently Nick Privinger dug up his PDF file and sent this to me. This is the abstract that he published in the SPOC conference. If you cannot see it, it's a blown up version. At the bottom, you see the Polymatroid axioms. And he asked precisely this question that as I presented to you. Okay, finally, I would like to make a few acknowledgments to thank my co-authors on this subject. The first one is Yeung of University of Southern California. Without his ingenious discovery of the first non-Shannon-type inequality, I probably won't have a chance to give a talk here today. And not also that, the technique that he invented for proving that non-Shannon-type inequality remains the only tool, be it computationally or analytically, the only way to discover non-Shannon-type inequalities after more than 10 years. Okay, another person I would like to thank is my former master and PhD student, Terence Chan. It has been a pleasure and privilege to work with him. And the third person actually is not my co-author, is Imre Chisser. The reason why I thank Imre is because he actually was responsible for connecting Zheng and myself to Ferro Matouche, who, with Milan Studeny at the Czech Academy of Science, were looking at the conditional independence problem from the point of view of Bayesian networks. Okay, so I would like to thank Imre for that. And that comes to the end of my talk. Thank you for your attention.
Thank you for a wonderfully informative talk, Raymond. And we have time for some questions. So there are any questions from the audience? Looking around. I don't see any hand. I don't see anyone jumping up. All right, then I'll do my duty of asking one question, which is the balance condition. It seemed to me perhaps was just another way of saying that in order for an inequality to hold for sure with respect to the differential entropies, that you needed to cancel out all the expected log Jacobian terms so that
basically that's the idea. Although you have to work out some details, but that's the basic idea. Yeah.
All right. Well, with no further ado, then let us thank Raymond once again for an excellent talk and move on.